Welcome to YouTube channel scientific_math. This is our second lecture on eigenvalues and eigenvector. The link of first lecture is available in video description. You can watch. Okay. So the learning objectives of second lecture is describe eigenvalues geometrically and algebraically. Second, the properties of eigenvalues, and the third one is theorem on eigenvalues and eigenvector. Okay. So and we also solve example how we can compute the eigenvalues and eigenvector of a given matrix. Okay, so let's start today lecture. Eigenvalues and eigenvector. Okay, so we again first discuss the definition of eigenvalues and eigenvector, and then we studied in detail. Okay, so definition eigenvalues and eigenvector. Let A be an n cross n square matrix, then a non-zero vector x in Rn means a real coordinate space of dimension n. Okay, so x be a non-zero vector for which this multiplication or this operation, that is the product of the matrix A and the vector x, which is equal to some scalar lambda and the vector x. Okay, so here we have the vector x cannot be equal to 0. Okay, we will discuss later in detail why this cannot be equal to 0. Okay, so here lambda is an eigenvalue of the matrix A and x is called an eigenvector that is associated with the lambda eigenvalue. Okay, so the set of all eigenvalues of an n cross n square matrix A is denoted by the this one and is known as the spectrum of the matrix A. Okay, so this is the definition of eigenvalues and eigenvector. Here we have studied this one is the operation and the vector x cannot be equal to 0 in any case. Okay, so the eigenvectors of the matrix A are those vectors x for which the multiplication by A results in a vector. Okay, here we can see that the product of this one is again a vector with the scalar multiple in the same direction or opposite direction to the vector x, and since the zero vector has no direction, this would make no sense for the zero vector. Okay, so that's why we say that the vector x cannot be equal to 0 because the zero vector has no direction and this make no sense. Okay, so next let's look at eigenvectors in more detail. Suppose we have the operation that is the vector that is the product of matrix and the vector is again a vector. Okay, so we write this one like that. Okay, we can take this one is equal to left side of the equal, and this is equal to this one, and this one is equal to this one. Okay, so we here took the vector x common. Okay, next, for some non-zero vector means for some x is not equal to 0, equivalently we can write this one. Okay, so here we have this is our first equation. Okay, when we are looking for eigenvectors, we are looking for non-trivial solution, means non-zero solution to the this equation. Okay, so this equation, this is our homogeneous system of equation. This is homogeneous system of equation. Homogeneous system of equation. We know that the solution to a homogeneous system of equation consists of a basic solution and the linear combination of those basic solutions. Okay, so in this case, we call the basic solution of the homogeneous equation the that is the basic eigenvector. Okay, we call the basic solution in this case basic eigenvector. Okay, it follows that any non-zero linear combination of basic eigenvector is again eigenvector. Okay, so suppose that the matrix, this one is the matrix, when we compute this operation, we get again a matrix. Okay, so suppose the matrix is invertible, means this matrix have inverse, so that this one exists, inverse exists, the inverse of this matrix exists, then the following equation would be true. Okay, so we can write like that x is equal to identity matrix into x, and we can write this one as, when we multiply this will give us again identity matrix, so we can write this one as. Okay, so now we multiply this with this one and we separate this one. Okay, so here we can see that this is equal to 0. Here we can see that this is equal to 0. Okay, so inverse of this matrix with 0 is equal to 0. Okay, this means x is equal to 0. Okay, so this claims that x is equal to 0. However, we have required that the vector could not be equal to 0. So this means, therefore, this matrix cannot have an inverse. Okay, so that's why we took the vector not cannot be 0. Okay, so non-zero vector, we non-zero vector. Okay, so we know that if a matrix is not invertible, then its determinant is equal to 0. Means, okay, the matrix will have determinant is equal to 0. Consequently, we conclude that the determinant is this matrix is equal to 0, means this matrix has 0 determinants. That's why the matrix have not inverse. Okay, so we can write also this one like that, both are equivalent, and this is the characteristic equation. Okay, so next we can write this one as, we can see that this is our matrix lambda minus I minus lambda into I minus A, and the determinant of this one is equal to this one. We can write this one like in this way. Okay, which is equal to 0. Oh, so next, the expression determinant of the matrix is called a polynomial in variable x. Okay, so when we solve this matrix for determinant, this will give us a polynomial in the variable x called the characteristics polynomial of A, and the determinant of, when we put this equal to 0, this will be the characteristic equation. Due to this, we also called eigenvalues of A as the characteristics value. So next we have definition of algebraic multiplicity of an eigenvalue. Let A be an n cross n matrix, square matrix with the characteristics polynomial given by the determinant of this one. Okay, so means characteristics polynomial, when we solve this one we will get a polynomial, then the multiplicity of eigenvalues lambda of the matrix A is the number of times lambda occur as a root of that characteristics polynomial. Means the number of we have lambda which is equal to lambda 1 is 1, and lambda 2 is equal to 1, and lambda 3 is equal to 2. Okay, so in this case we can see that lambda 1 and lambda 2 both are same. This means the we have the algebraic multiplicity of eigenvalues is 2. Means we can see that here the lambda 1 is a repeat two times. Okay, so the number of times lambda occur as a root of that characteristics polynomial. Okay, next we have the definition, that is the geometric multiplicity, and here we have the number of distinct linearly independent eigenvectors. Okay, for a particular eigenvalues is known as the geometric multiplicity. Okay, so algebraic multiplicity always greater than or equal to the geometric multiplicity. Okay, now we discuss the properties related to the eigenvalues. Properties. Eigenvalues of a Hermitian matrix are all real. We know that what is Hermitian matrix. We have already studied in earlier lectures about the types of matrices. I will provide the link in video description. You can watch. Okay. Second property, we have the eigenvalues of a few Hermitian matrix are either zero or purely imaginary. Eigenvalues of orthogonal matrix are unit modulus. Eigenvalues of idempotent matrix, this is the idempotent matrix, are either 0 or 1. Okay. Eigenvalues of unitary matrix are u of unit modulus. Eigenvalues of an involuntary matrix are either plus 1 or minus 1. Okay, so if A and B are two matrices of same order, then A and B have eigenvalues where B is equal to uh, P inverse with A and multiplied with the P. Okay, so P is any matrix whose inverse exists or similar matrices have same eigenvalues. Okay. Next we have, if lambda is an eigenvalue of the matrix A, then lambda inverse is an eigenvalue of the inverse matrix, provided that the determinant cannot be equal to 0 of that matrix. Okay, next we have the eigenvalues of adjoint of A, which is equal to the determinant divided by the eigenvalue. Next, the mat the matrix A and its transpose have the same eigenvalues. Matrix A and its transpose have same eigenvalues. Same eigenvalues. Okay. Next we have, if lambda 1, lambda 2 up to lambda n are the n eigenvalues of a square matrix A, then eigenvalues of Ka means when we multiply the matrix A with some scalar number, uh, so then the eigenvalues of that matrix will be k into lambda 1 means k into lambda 1, k into lambda 2, and k into lambda n. Okay, so and the eigenvalues of the inverse matrix will be 1 by lambda 1, lambda 2, and lambda n. And eigenvalues of the A square will be the square of that matrix. Okay, next, any two eigenvectors corresponding to the two distinct eigenvalues of a unitary matrix are the real symmetric matrix A are orthogonal. Okay, orthogonal. Okay, so theorem, we have a theorem, and what is the theorem? The product of eigenvalues of the matrix is equal to the determinant of that matrix. Means we have a two eigenvalues lambda 1 and lambda 2. Okay, so the product of this one will be equal to the a given matrix equal to the determinant of the given matrix, and sum of eigenvalues of the matrix will be equal to the trace of that matrix. Means lambda 1 plus lambda 2 will be equal to the trace of the matrix A. Okay, means we have matrix A is A11, A12, A21, and A2. So what is trace? Trace is the sum of diagonal values. A11, which is equal to A11 plus A22. Okay, and this one product will be equal to the determinant of that matrix. Okay, so thank you so much for watching my video about the eigenvalues and eigenvector. That is our second lecture about the eigenvalues and eigenvector. In next lecture, we will studied how to find the eigenvalues and the eigenvector, and we will also uh, discuss with the help of graphical representation. Okay, so thank you so much for watching my video. Please subscribe my channel scientific underscore math.